If you recall, the two major prongs of inferential statistics are estimation and hypothesis testing. So far, we've talked about estimation. We've talked about point and interval estimates. The idea of inferential statistics is that because we can't always collect all the information about a population, we gather a random sample from a population, and then we use what we know about sampling variability. And this, the central limit theorem tells us that a distribution of sample means is in fact normally distributed, centered on the population mean mu, symmetric, and it has a particular spread that we call the standard error of the sample mean, which is given by sigma divided by the square root of n. Using all of this, we can create interval estimates, not only point estimates. Well, the other big prong, the other big part of inferential statistics is hypothesis testing. Often people will make claims about the population, and you can use a sample of data to test that particular claim. We're going to explore the basics of hypothesis testing here, some of the fundamental concepts. But in the coming lectures, we will revisit this topic of hypothesis testing over and over and over. So for now, the idea is to get some of these basic concepts out of the way and really kind of understand some of these ideas. But we're going to revisit these ideas over and over and over. So the very general outlines of hypothesis testing, you start with some claims and you express these claims in terms of hypotheses. We call a null hypothesis H subscript 0, or H naught, sometimes people call that. And we call the alternative hypothesis H subscript A. Then what we do is we collect some evidence, data, and then we assume the null hypothesis is true. Right? Intuitively, the null hypothesis is typically, not always, but typically something, it's kind of the default state of affairs. It's something that nothing interesting is going on. It's, in terms of a legal context, it's like assuming the defendant is innocent, right, until proven guilty. Well, we assume the null hypothesis is true. We assume, in general, nothing's going on. And then we make a decision based on the evidence. If there is sufficient evidence, we reject the null hypothesis. So in the legal context, you might say the defendant is guilty. We reject the null that the person is innocent. Right? If there is not enough evidence, then we fail to reject the null hypothesis. So we conclude the defendant is in fact not guilty. So let's look at this example of aerobic conditioning. So suppose an investigator wants to study whether or not Harvard Extension students have similar aerobic conditioning as the general US population. The general US population, it is known that the mean heart rate is 69 beats per minute with a standard deviation of 6 beats per minute. So we have this value of mu and this value of sigma, the population standard deviation. So we would like to gather a group of 20 students who are attending STATE100 in order to investigate this thought. Okay? We will use a confidence interval for our hypothesis test for now. Right? So first of all, we might ask, do we think this sample of STAT100 students is a good random sample of the target population? Well, the target population consists of all Harvard Extension students. So the subset of STATE100 students, it could be a good random sample of our target population, but it may consist of a higher proportion of highly motivated students who may differ from the population of Harvard students at large. Key point is that for now we're going to treat this as a pretty good sample of our target population. The next thing, after these sort of preliminary considerations are done with, we want to set up the null and alternative hypotheses. So the null hypothesis, as I mentioned before, it's denoted by H subscript 0, H naught, and the alternative is denoted by H subscript A. The null, typically, null is nothing, right? Typically the null is not much is going on, So it's whatever the default state of affairs. Hypotheses, they can be one or two-sided or tailed. For now, we're going to consider what we call a two-sided test. We're going to look at this in more detail, but for now, we're going to think in terms of a two-sided or two-tailed test. For this kind of hypothesis test we're examining right now, right, we want to test some claimed value for the population mean. So the null is that the population mean equals some claimed value. The claimed value of the population mean we express as mu subscript 0 or mu naught. Right? Somebody might say, I think the mean in the population is 20. So the null would be mu equals 20. Another person might say, I think it's 0. In that case, the null would be that the population mean mu is 0, right? The key point is that when we set up the hypothesis test, the null is an equality where we think the population mean equals some claimed value. Often that claimed value is a default state of affairs. It's not very interesting if the mean is 20, let's say. Then in a two-sided or two-tailed test, the alternative hypothesis is that it's simply not that claimed value. Right? That's what that equal sign with that sort of diagonal line through it means. It means not equal. So if we think that if somebody thinks that the population mean is 20, the null would be that mu equals 20, and the alternative would be that mu does not equal 20. Right? This is sort of the basics of setting up the null and alternative hypotheses. Then what we do is we assume the null is true. Right? We assume that the sort of nothing going on claim, it's not always nothing is going on, but typically the null is, it's not that interesting. We assume that that's true. We assume that just, nothing unusual is going on. Right? And then what we do is we collect evidence with the idea of, we want to see if we're going to reject the null or not. Right? That is our goal with this kind of analysis. Right? The key point, though, is that we can reject the null hypothesis or fail to reject the null hypothesis. If we reject the null, then by extension, we accept the alternative hypothesis. Or we can fail to reject the null. We can say we don't have enough evidence. Now, you must understand, there isn't an option of accepting the null hypothesis. This is because this kind of hypothesis testing framework, it's based on the logic of scientific inference, in which it is easier to disprove something than to prove something. So let's go back to this idea of aerobic conditioning for students at Harvard. So the investigator wants to study whether or not Harvard Extension students have similar aerobic conditioning as the general US population. So we're using this sample of STATE100 students to make a generalization about, or to rather test a claim about the US population vis-a-vis the Harvard Extension School population. And we know for the setup that in the US population, we know the population mean is 69 beats per minute. And we know in the population of all people living in the United States, the standard deviation is 6 beats per minute. So we want to use this sample set of data to investigate this claim. Right? So first of all, what are the hypotheses? Right? We're going to set up a two-sided test. And the claimed value here is that the mean heart rate is 69 beats per minute. So somebody's claiming, I think the mean heart rate at Harvard, it's just the same as the mean heart rate among all people living in the United States. So the null is that the population mean of Harvard students equals 69 beats per minute. We get that value of 69 beats per minute because that's the value of all people living in the United States. Then since we have a two-sided test, the alternative is that that mean of Harvard students, it's not equal to 69. Maybe Harvard students are in fact less aerobically conditioned, and so maybe their heart rate is actually higher. Or maybe they're more aerobically conditioned, so their heart rate is lower. We don't, we're not making any sort of alternative claim, whether it's above or below, but the point is that we think that it's just different. We think Harvard students are perhaps different than that for the US population in terms of aerobic conditioning. Then we collect this data based on STATE100 students to test this claim about the population. Right? This is the basic setup for hypothesis testing. Somebody makes a claim about a population, you gather a set of data, and you test that claim. We're testing the claim whether or not the population mean of Harvard students is 69 beats per minute or not. So we're going to see if we can reject that null or not. Now before we do that, you should keep in mind that there is a possibility of making an error here. We can make two kinds of errors. First of all, we could reject the null, but the null might in fact be true. We call that a type 1 error or sometimes an alpha error. It's also possible that we could fail to reject the null when in fact the null is false. We call that a type 2 error or sometimes a beta error. Now you can see here that it's possible, we can either make a correct decision or an incorrect decision. The two correct decisions would be if in fact in reality the null is true, and we fail to reject the null. That's a correct decision. Or it's possible the null is false in reality, and our decision is that we reject the null. In that case, we also make a correct decision. But the two errors occur when we reject the null when it is true, and we fail to reject the null when it is false. We call these type 1 and type 2 errors, respectively. Now, type 1 and type 2 errors, it's easy to get these mixed up. So I offer two mnemonics. A mnemonic is just a device that helps you to remember something. So for example, the colors of the rainbow are Roy G. Biv, red, orange, yellow, green, indigo, blue, and violet. Or the order of the planets. My very excellent memory just served up 9 planets. You take the first letter of that phrase, you got the order of the planets. But of course, Pluto is no longer a planet, so that doesn't work. But the point is that you have to just remove that last word. The point, however, is that a mnemonic is just a tool. So people often get confused type 1 versus type 2 errors. So there are two mnemonics I like to point out. First of all, you can think of a type 1 error as a false alarm, right? A type 1 error is when, in fact, it's a false alarm. It's like saying, there's a fire in the movie theater, when, in fact, there isn't a fire in the movie theater. A type 2 error is just saying, oh, there isn't a fire in the movie theater, but, in fact, there is a fire. Maybe there's a fire behind the movie screen. The point is that you have these two kinds of errors. Well, a type 1 error, it could be considered a false alarm. And if you add up all the letters of false alarm, there are 10 letters there. A type 2 error can be viewed as a misdetection. And if you add up all the letters for misdetection, you have 15 letters. Well, 15 letters is greater than 10 letters in the same way that 2 is greater than 1. So that misdetection has more letters, that's associated with a type 2 error. False alarm has more letters, has fewer letters rather, and that's associated with type 1 error. Another mnemonic sometimes people like to think of is in terms of false positives or false negatives. Right? Type 1 error is sometimes called a false positive, and a type 2 error is sometimes called a false negative. Well, a type 1 error, has one vertical line for 1, just like the letter P. Thus, a type 1 error is associated with a false positive. Type 2 error, well, it has 2 vertical lines, just like the letter N. You can think of letter N with 2 vertical lines. Thus, a type 2 error is associated with a false negative. Now, sometimes people don't need to use these mnemonics. Sometimes people prefer their own mnemonic. But in general, it's very easy to confuse a type 1 versus type 2 error. And so I recommend using one of these two mnemonics. I prefer the false alarm versus misdetection terminology, but you can use whatever mnemonic you find useful. Now, the key point here is that you might think, what is worse? Type 1 error, a false alarm, or type 2 error, a misdetection? Well, sometimes people find it useful in the context of the law. So you can think of an innocent person being correctly declared, or you can say that guilt is correctly declared. But then you also have these two other scenarios in which a guilty person is incorrectly set free, or an innocent person is sent to prison. Now the question you might say, well, which one is worse, false alarm or misdetection? One is not necessarily worse than the other. This is a subjective judgment on the costs involved. And often when we conduct hypothesis tests, we're interested in whether, are we concerned about a false alarm or misdetection? I think in general in the social sciences, people are a little bit more concerned right now about false alarms. Right? There are just incentives to say something is going on when in fact nothing is. For example, a drug company, they have an incentive to say a drug works. They have an incentive to reject a null that a drug is the same as a sugar pill. Right? So there is a problem about too many type 1 errors. Well, once we kind of set up the hypotheses and consider the possibility of type 1 and 2 errors, we're going to gather our data and we're going to calculate a confidence interval. Right? We can use confidence intervals, in fact, to test hypotheses. If a confidence interval, if it doesn't include the claimed value, then we can reject the null hypothesis in a two-sided test context. If a confidence interval does in fact contain the claimed value, then we can fail to reject the corresponding null hypothesis tests. One way to think of confidence intervals, it can be viewed as a measure of consistency. If the confidence interval contains the claimed value, then it's consistent with that value, and we fail to reject the null. So let's go back to this example of aerobic conditioning. Let's collect a 95% confidence interval. So 95% confidence interval is simply our point estimate plus or minus 1.96, so that's our value of z star, because when we have plus or minus 1.96, right, we're going to capture 95% of those sample means around the population mean. So our point estimate is the sample mean of 60.11, and we're going to add and subtract 1.96 times the standard error. And when we do that, we have a sample size of 20 people. When we do that, we have this interval of 57.48 to 62.74. So we're 95% confident that true population mean heart rate is in that interval. That 95% confidence interval does not include the Null mean of 69. Because keep in mind, if the Null is that the mean heart rate of Harvard students is the same as that for the overall population of people living in the United States. So the claim is that mu for Harvard students equals 69. Well, in fact, this confidence interval is much lower, right? Which suggests that Harvard students are more aerobically conditioned based on this sample of data. So in this case, we reject the Null that Harvard students have a mean of 69. And I think the key point here is that you might say, well, just consider, how would a 90% confidence interval compare to ours? How would a 99% confidence interval? Well, again, a 90% confidence interval would be narrower, while 99% confidence interval would be wider. So, we can sort of alter our consideration here based on the level of confidence. The key point is that in this case, with a 95% confidence interval, we in fact reject the null hypothesis. Now, there's another way of testing and evaluating some claim. This is based on the idea of probability values, or p-values. We're going to explore this in more depth, but for now, I just want you to understand the basic concepts of a p-values. Right? A p-value, or probability value, it's simply the probability of obtaining data as or more extreme than the data we actually observed, assuming the null is true. If you recall, I said, we can kind of think of the confidence interval as a measure of consistency. Right? If the null is within our confidence interval, right, the null is consistent with our data, and we fail to reject the null. Right? If that null is outside of our confidence interval, then that suggests our data is somehow inconsistent with our null hypothesis, and we reject the null. Well, another way is to kind of measure consistency between our data and our null hypothesis is with p-values. A p-value, or probability value, tells us how consistent the observed data are with the null hypothesis under the assumption that the null is true. P-values, or probability values, as they suggest, they range from 0 to 1. Right? A small probability value indicates that the observed data and the null hypothesis are really inconsistent. It's a low p-value or small p-value. It suggests that the probability of obtaining the data we have under the assumption that the null is true, it's really unlikely. They're really inconsistent. Whereas a large p-value closer to 1, it suggests that the data are consistent with the null hypothesis. If you assume the null to be true and you get a p-value of 1, it suggests that they're consistent with each other. So we'd fail to reject the null hypothesis. The mnemonic you should burn into your brain is that if the p is low, the null must go. So you might say, what is a low or small p-value? Well, we have this standard cutoff for making a decision in a hypothesis test context. We reject the null hypothesis when the p-value is low, usually defined as smaller than alpha equals 0.05. Alpha here we call the alpha criterion level. This is just by convention, right? And typically we use software to calculate p-values, right? P-values are very commonly used in scientific articles. For this aerobic conditioning example, using statistical software, I calculated the p-value to be 0.00001. So the probability, right, of obtaining the data we have under the assumption that the null is 69 beats per minute, it's very unlikely. And this p-value is lower than the alpha level of 0.05, so we reject the null hypothesis. But how do we get this level of alpha equals 0.05? Well, it comes from an offhand comment by R.A. Fisher, one of the founders of modern statistics. In 1925, in an article called Statistical Methods for Research Workers, he said the value for which p equals 0.05, or 1 in 20, is 1.96 or nearly 2. It is convenient to take this point as a limit in judging whether a deviation ought to be considered significant or not, statistical significance. The key point here is that this is a guideline. This is not a law of nature. And we're going to work more with p-values in the coming lectures. For now, I just want you to understand the basic concept that you can think of confidence intervals and p-values they kind of tell you how consistent or inconsistent our data is with the null hypothesis under the assumption that the null is true. So just to show you how important probability values in this process of gathering data, assuming the null to be true, and then comparing, seeing how consistent or inconsistent our data is with the null, how important this process is. I want you to look at this example of the Higgs boson particle, in which they use p-values to make a decision about a scientific theory. So in 2012, physicists, they announced the results for finding what they called the Higgs particle. Right? They used data from a particle accelerator in Europe to gather data, and then they assumed that the particle didn't exist. That was the null hypothesis. They gathered data, and then they calculated the probability of obtaining the data they in fact obtained under the assumption that the particle doesn't exist. And so they calculated p-value. Now, the technical details, they're highly specialized to physicists, but even at this point, their conclusion on finding the particle is based on statistical inferences, right? Just the basics of it. Rather than referring to a p-value, probability value, they expressed their cutoff in terms of sigma levels, right? So instead of an alpha of 0.05, which you might call 2 sigma, what they did is they used this cutoff level of 5 sigma. So when they talk about 5 sigma, they're just referring to this very, very low level of alpha as a cutoff. They said, we find a p-value lower than this alpha level, which they call 5 sigma, then we're going to say that there is this Higgs particle. We're going to reject the null that it doesn't exist. Right? That's the key point. The key point is that what they do is in essence, they calculate a p-value after assuming the null is true, right, based on this set of data. And so I want you to look at their reaction, right, to using the basics of statistics to come to a conclusion.
This is a very, very preliminary result, but we think it's very strong. It's very solid. Otherwise, we wouldn't present it. And we've slowly, as we've gathered data, rediscovered the standard model to more and more rare processes, and basically we're very confident now that we can go after the rarest, which is the Higgs. If we combine the ZZ and gamma gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations.
Should I say that I'm pleased?
Congratulations.
I think it's obvious.
This is still mine, right?
This is yours, yes.
As a layman, I would now say, I think we have it. You agree? Yeah.
Now you might ask, after watching this video, why are people crying or fainting almost and erupting in applause from p-values? Are they crazy? No, it's because statistics can tell us facts about the world we never knew before. This idea of statistical inference, it's unbelievably powerful and useful. And with that, we will conclude our discussion so far for inferential statistics. We've just talked about the basics of sampling in terms of the distribution of sample means. We've also talked about point and interval estimates. And we've also talked about the basics of hypothesis testing. We're going to revisit all of these topics again and again in the coming lectures. And with that, we conclude our discussion of the sampling distribution.